Welcome to the first tutorial in a series on trigonometry at the higher level. Now, I'm actually recording this series on trigonometry sort of interspersed with some lectures on calculus because I want to talk about the derivatives of the sine and cosine functions, but I don't just want to write down some formulas. I want to motivate them for you, and it's easier and more useful to motivate them once we've seen a little bit more trigonometry than we've studied heretofore in the National 5 lectures. If your trigonometry is a little bit hazy, then you might want to just review the National 5 level trigonometry. There's a whole series of tutorials at that level, and I'll put the links in the description below. So in this first tutorial on trigonometry at the higher level, I'm really going to talk about one concept which at one level is very simple. At another level it can be a little bit confusing, and this is to do with what units do we use to measure angle. And you might say, well, we know the answer to that. We use degrees, and there are 360 degrees in a circle, and there are 90 degrees in a right angle, and so on. And that's perfectly fine. Degrees are a very familiar and useful way to measure angles. The issue is, though, that there is a natural unit of angle that mathematics knows about and in a sense demands that we use once we start thinking about sine and cosine as functions, and particularly once we start doing calculus with those trigonometric functions. There is a unit of angle that I would say is sort of intrinsic to the mathematics and is not a human choice, whereas degrees are absolutely a human choice. The notion of 360 degrees in a circle, I believe, goes all the way back to the Babylonian Empire, where the Babylonians, I think very smartly, tried to use number 60 as sort of a base in their calculations, because 60 is a really easy number to manipulate. It has many, many factors. So I believe that's the basis of our 60 seconds in a minute, 60 minutes in an hour, and also the kind of the root importance of the number 60 in our choice of degrees. 60 degrees in an equilateral triangle's angle, and so on and so on and so on. However, it is a human choice, and we take it for granted because we learn it so young that it just becomes the natural way for us to talk about angles. However, it won't cut the mustard when we are doing calculus, because it turns out that mathematics intrinsically has a preferred choice, which is not degrees. So I'm going to tell you what that preferred choice of mathematics is, and then connect it to degrees, and that will provide you sort of with a key in the future. There's no problem thinking about degrees in a sort of casual way, but formally you need to always be able to connect it to this natural unit of angles. And that natural unit goes under the name of radians. All right, and let us see, using an example of a circle, how we can motivate radians as a sort of human-free choice of unit of angle. So I'm going to draw a circle here. Let's see. All right, there's a circle, and I'm going to keep that radius I chose with my compass handy for a moment. And I'm going to be pretty careful here, so I'm going to actually use a ruler, and I'm going to draw an arbitrary radius coming from the center of this circle to the circumference, and that line has a length, the radius of the circle. Let me call that little r. All right, there's the center of the circle there. Now, this is quite pretty. There is a very natural way to define sort of a unit of angle which requires no more information than what I've got here, and that is to define an angle where we travel along an arc a distance of 1 radius. Okay, so let me take this little piece of thread here that you can see. I put one end at the center, and I'm just going to mark on the thread, that's 1 radius there. Okay, sort of marked it on the thread. That's my yardstick, and I can just check. You see, I can just put it against here and just check that that is, yep, that's 1 radius. That's fine. And I'm going to use this piece of thread to measure out one. This is going to be not exact, of course, but fairly good. I'm going to mark out, let this thread follow the circle the best I can, and mark off roughly where the piece of thread ends there. Okay, that thread wasn't actually the most brilliant way to do this, but it's good enough. So the distance around here, let me try and indicate that by just doing a little sort of arrow here. Yeah, so this distance along the edge of the circle, this arc length here, is also r. And then let me just connect here. So I'm not making a triangle, I'm making sort of a pie slice. Okay. A sector of a circle there where the 2 straight lines are just radii, and then the arc has a length of 1 radius. And that angle contained therein is 1 radian by definition. So this angle is 1 radian. All right. And now what we want to do, having seen how we define a radian, is connect this. Well, how many degrees is that? And there's a nice way that you can see that, which is the following. If I go all the way around the circle, let's call that 1 revolution. So 1 revolution is, we know in degrees, 360 degrees. What would 1 revolution be in terms of this unit of angle, the radian? Well, we can easily see that because we know the circumference is 2 pi times the radius. So the distance around the circle from start to finish is 2 pi times the radius. That is also 1 revolution. And because a radian of angle takes us 1 radius around the circumference, therefore 1 revolution is going to be 2 pi lots of radians. I hope that's understandable. So one unit of angle, 1 radian, takes us a distance r around the circle. If we go 2 pi lots of r around the circle, that's 1 circumference, that's exactly 1 revolution. Therefore 2 pi lots of this unit of angle, the radian, will be 1 revolution. So that gives us our conversion now, because we can just compare these 2 measurements of a revolution, a full circle, in terms of degrees and radians, and we have that 2 pi radians is equal to 360 degrees. So that's one way to think about connecting radians to angles. If I divide by 2 pi, I see that 1 radian is 360 degrees divided by 2 pi. I can divide top and bottom by 2. Well, so I have a common factor of 2, and then I have 180 degrees divided by pi. And that's probably, I would say, the best way to think about connecting a radian to degrees is using that conversion in the box there. All right. Now, I think I have my calculator handy here. We can just work out, well, what actually is that number? So 180 degrees divided by pi gives us 57. This is roughly equal to 57.3 degrees. So this is not a number that I think you need to try and memorize, but it's good to have a rough sense that a radian is just a little bit less than 60 degrees, sort of 57 degrees. And in fact, I think I have a protractor here. We can just have a sense check. Does that all marry? Does that make sense here? If I put my protractor on there, yes, that looks actually remarkably good, in fact. So there's 50 degrees and 60 degrees, and you can see, yes, indeed, that angle looks to be, roughly 57 degrees. So the picture that I drew with my little piece of thread, I think probably more by luck than skill, is an accurate rendering of a radian. This is a more formal way to think about it, and a radian is indeed 180 divided by pi degrees. Right. So what we need to start thinking about in trigonometry and in dealing with sine and cosine functions at the higher level and beyond is that when we think about angles, we need to be thinking in terms of radians, not in terms of degrees, because when it comes to doing calculus, as we'll see, it is essential that one uses radians, because otherwise, if one didn't, lots of beautiful relationships would become sullied by endless tedious factors of 180 over pi, and you just don't want all those tedious factors around, because as you'll see, there's tremendous beauty in the calculus of trigonometric functions, and that beauty actually goes well beyond this level of maths, and at undergraduate level you would be studying certain properties of the calculus of sine and cosine that are really awesome, something that goes under the name of Fourier analysis, and maybe I'll give some lectures on that in the future. It's just stunning material. Right, so let me just end this tutorial by doing a quick sketch, if I can, of sine, cosine and tan, partly to remind you what those functions look like, but also it would be quite useful that I can label the x-axis with radians instead of degrees, and it would be kind of a useful way to start to cement this idea of radians. So let me see if I can do some reasonable sketch here. Okay, something like this. So this is going to be the x-axis for sine, for cosine, and for tangent. I would like to have a few dashed lines around here, so maybe something like this. It's quite tricky to kind of squash all of these onto one page, but we'd try our best here, and I hope you don't mind me just sort of doing this in real time. Give you a chance to sip your tea while you're watching, and you can always fast forward if it gets a bit boring. All right, so that's going to be good enough, I think. So I'm going to draw sine on here, and it goes between -1 and 1. I'm going to draw cosine on here, and that goes between -1 and 1, and I'm going to draw tan on here. And let me write these angles down in radians. This is the equivalent of 360 degrees, because I'm going to draw one full cycle of these sine and cosine functions. So 360 degrees is 2 pi radians. So in radians now, this angle has a value 2 pi. Maybe I'll put that on every graph, and that way it will be clearer. 180 degrees is pi, okay? And then I really, just try and get fluent with these conversions. So 90 degrees will be pi over 2, and that's a really good one to try and remember as well. Pi over 2, pi over 2, pi over 2. And then 270 degrees is 3 pi over 2. You don't have to memorize all of these, because the thing is, I think if you're happy with 2 pi being 360, pi being 180, pi over 2 being 90, then really any other angle you can quickly infer just by doing a bit of mental arithmetic. All right, so for example, 45 degrees, which lies there, would be pi over 4. I'll just write down a couple of other ones which are quite useful. So if I say pi over 2 radians is 90 degrees, then you can see that pi over 6 radians, I'll just put R for radians, it's a bit sloppy, but I don't have room to write rad. Pi over 6 radians would be 30 degrees, because it's a third, and then 2/3 of this would be pi over 3 radians is 60 degrees. So those are quite good ones to sort of have in mind too. And as I mentioned, pi over 4 radians being 45 degrees. Over time these will become very familiar, but I think at the outset, as I mentioned, pi is 180, 2 pi is 360, pi over 2 is 90 are the kind of important anchor points that I think you just want to have to hand, really. Right, and let's just remind ourselves what these trigonometric functions look like. So I've got sine starting at 0 radians, not 0 degrees, I'm going to say 0 radians. It hits 1 at pi over 2, it comes back down to 0 at pi. And then goes -1 at 3 pi over 2, and back to 0 at 2 pi. There is our function sine x in radians. Cosine starts at 1 at 0 radians, passes through 0 at pi over 2 radians, and is -1 at pi radians. And then goes back up like that, passing through 0 at 3 pi over 2 radians, back to 1 at 2 pi radians. And these functions will repeat in this direction and in this direction, repeating every 2 pi radians. All right. And finally, tan starts at 0 radians, shoots off to infinity at pi over 2 radians, comes back in from -infinity, passes through 0 at pi radians, off to infinity again at 3 pi over 2, and then comes in again just after 3 pi over 2 from -infinity back to 0 at 2 pi radians, and likewise repeats. That's tan x, which, just to remind you, is the ratio of sine x over cosine of x. All right, so that's, I just need to shift that up a wee bit there. That's a reminder of those functions sine, cosine, and tan. And just remember that tan, in the old currency of degrees, this function repeats every 180 degrees. So in radian language, tan would have a period or a repetition of pi radians. It repeats every pi radians. Phew. Okay, so that's an introduction to radians. It's a bit like going from sort of pounds and ounces to kilograms and grams. Pounds and ounces are a really, for people in the US and in the UK, a really handy way to think about everyday weights and measures. But if you were doing science, it's more convenient to use a system based on powers of 10, and so we use grams and kilograms and so on. This is a bit more profound because degrees are a human choice, but radians are not a more convenient choice. We don't use radians because we have 10 digits. We use radians because maths knows that it has a preferred angle, as we'll see when we do calculus. And it comes from this very beautiful sort of construction that when you draw a circle, there is sort of a natural choice-free angle that you can construct, as it were, which is the radian. Good. Right, so that's fine. I'm going to record a second lecture in this series on trigonometry at the higher level, and that is going to be on some very interesting formulae called the addition formulae, and we're going to use those when we start looking at the calculus of sine and cosine. So thank you very much indeed, and I'll see you next time.